Okay, so we're going to continue our series of lectures on metabolism, and now we're just going to look at more in depth the mechanisms in metabolism and specifically how insulin and glucagon act on the body to regulate glucose concentration, and that will set us up nicely for the next lecture on diabetes. To get glucose into the body, we've got these two different ways. So we've got these sodium dependent transporters, SGLT1 and SGLT2, and they basically work by allowing glucose to enter the body, going up its concentration gradient. So because glucose here, as you can see in the diagram, enters, one sodium ion will enter as well, and this will cause glucose to then enter through GLUT2 into the blood. And because now we have a net positive because of this sodium ion coming in, we've got this sodium potassium ATPase balancing out that charge by allowing one potassium ion to leave the blood and then into the lumen, and that balances out the charges. Then we have these sodium independent, such as these GLUT2, as you can see here, and they're all specified to a specific part of the body. So we've got GLUT1, which enters erythrocytes, GLUT2 hepatocytes, so liver cells and pancreatic cells. GLUT3 is your brain neurocell, and GLUT4 are your adipocytes and muscle cells, and they're quite insulin sensitive, and we'll look into what that means later on. So if we talk about different isoforms here of these kinases, so we've got hexo, which are found in erythrocytes, and glucokinases found more in hepatic cells. Because your blood is kind of the first place where glucose comes in, we've got this hexokinase which has a very low Km, and the lower the Km, the higher affinity the enzyme has for the molecule. So this means that glucose will be quickly transformed or broken down by this hexokinase into the glucose 6-phosphate that we talked about in the last lecture. So this works at very low glucose concentrations, meaning allowing glucose not to build up too high. But again, we've got liver, so this works kind of progressively as the glucose concentration does increase, as a kind of a backup for hexokinase. And glucokinase works at much higher glucose concentrations, and being there as a backup in case the glucose does rise too quickly. And so if we talk about the hormones, so we've got on the left here we've got beta cells of insulin, and on the right we've got the alpha cells at the islets of Langerhans in your pancreas. And alpha cells, so I always remember alpha A has an A in it and glucagon has an A in it. So that's why alpha cells secrete glucagon and beta cells therefore secrete insulin. So if we just do a little roundup of how insulin is made, so we've got this pre-proinsulin form, as you can see in the diagram here. This is then cleaved to remove this signal peptide, and now it's called proinsulin. And then we chop off this top bit here, we cleave this top bit here, and at the same time we can see here these sulfide bonds forming a sulfide bridge of the molecule, and then when we cleave here in the proinsulin, we remove the C peptide here, C chain, and now we've got a mature molecule here with our sulfide bonds. This insulin is then stored as hexamers around a zinc molecule, and so I mean to eat our zinc. Along with it, the free peptide will be there and be in those vesicles as well. And this happens obviously inside the cell, so it's always good to have an overview feel for where all of this is happening, because we can get too involved in these mechanisms and kind of forget that it's all part of a big system and it's not just an isolation. So what happens when then glucose enters the cell and and glucose concentration increases? How does the body deal with that? So in the cell, glucose will increase the concentration. Therefore, more glycolysis and oxidative phosphorylation will occur to deal with this glucose and use it up. This means more ATP will cause the potassium ATP A's in the cell membrane to stop working, and therefore membrane will depolarize. This will cause these voltage-dependent calcium channels to open up, and therefore calcium 2+ will enter and release the insulin vesicles that we just talked about in those hexamers, and they will exit the cell via exocytosis. So we talked about some cells, such as muscles and adipocytes, having this GLUT4 transporters, and which are insulin sensitive. So coming back to that now. So what happens when insulin binds to the receptors in the cells? We enter a signaling cascade via PI3 kinase, and this will cause these vesicles. So if you think about a cell, we've got a cell here. So inside we've got little vesicles which have on the inside GLUT4 transporters, and the cascade of the PI3 kinase will cause these to reach the surface of the membrane and attach to the membrane, like spread out, so all the receptors are now facing out, and this will allow glucose to bind to them and then enter from the blood into the cell and then be taken in by endocytosis. And then if we kind of zoom out a bit and talk about glucagon and adrenaline, so we can talk about how glycogen is broken down, so kind of going the other way, if it's needed in the body, to see how it's broken down. So it looks a bit complicated at first, but if we just go down the chain, we'll see what happens. So enzymes can be either, enzymes are phosphorylated and they can become active or inactive. In this case, if you see kinase, that usually means an enzyme that has kinase and it will phosphorylate another enzyme. So first what happens is the adrenaline or glucagon will bind to its receptor, and we have this adenylyl cyclase will activate change ATP into this CAMP, which will activate protein kinase A. This protein kinase A will phosphorylate phosphorylase kinase, activating it into this active form here, and then this will again happen, but phosphorylase kinase will then phosphorylate glycogen phosphorylase, making it activating it again. And as we talked in our previous lecture, glycogen phosphorylase is the opposite of glycogen synthase, and therefore this glycogen phosphorylase will break down glycogen into a smaller molecule of glycogen, obviously, but this glucose 1-phosphate molecule broken down. And obviously this can keep occurring until we have no glycogen left, and this N will always be -1 because we're removing one molecule of glucose. So what happens when insulin comes in? So as we talked about, glucagon and insulin kind of work against each other and try to stop each other from doing their own function, and also to keep our glycogen stored still in place, but still providing enough energy for the body in order for it to keep functioning. So when insulin comes in, it will again bind to a receptor of its own, and then in the lipid bilayer. And then there's an example of what happens when an enzyme is phosphorylated or dephosphorylated and then it becomes activated. So the insulin receptor causes this protein phosphatase to dephosphorylase, so a phosphate is removed, and that causes it to activate. This in turn, protein phosphatase will dephosphorylase phosphorylase kinase, meaning that this cascade now stops here, so glycogen phosphorylase can't be activated, and therefore glycogen can't be broken down further. So that means that storage of glycogen will be then favored, and this keeps happening. So if we've obviously got more glucagon, the more glucagon we have, the more of this cascade will occur at one time. But then as insulin comes in, it will slowly start to decrease the amount of glycogen that's broken down and slowly stop the cascade, so we don't use up all our glycogen at once. And this is a good way of having a kind of negative feedback of the body, so too much of one molecule isn't broken down. So I'm pretty sure, yeah, it's pretty much it. So yeah, thank you for watching, and in the next, I'm pretty sure we're going to be talking about diabetes and what happens when these hormones don't work as they should. So thank you, like and subscribe, and I'll see you then. Cheerio.